It doesn't start recording unless you stop screen sharing.
Okay. So yeah. So firstly, I guess we invert about ABC. Well, the circumcircle of ABC. So A, B, C, and the circumcircle, they're still like the same, I guess. So let's just do A, B, C. Where's the circle? Circles are really points. Okay, yeah, so these stay the same. And then we have P and Q lie on OB and OC respectively. So let's get the center of this. Where's the center tool? Center. This is O. Okay, this is still O, but like O is now at the point of infinity. But like that's fine. Wait, whoops. This is O. Okay, and then they're still on BO and CO because BO and CO pass through the center, so it's fine. So I guess P and Q, such that APOQ lie on a circle. So APOQ that circle passes through O, right? Which means that if you invert it, it's like a line through A. So I'm just gonna draw a line through A. Like there's no line in particular.
Well, which circle is this?
So APOQ lie on a circle. So basically, I just draw a line through A as that circle.
Oh yeah.
Inverted, and then P and Q goes on. I don't know. Well, which one's which? So yeah. So basically, I can move this line around. It's like a moving line, right? Yeah.
Oh yeah.
A P O Q. P is on OB and Q is on OC. So this is P and this is Q. Okay. This is P. This is Q. Okay. So now we have the P and Q. What about the M and N? So they're the midpoints. M is the midpoint of AB, N is the midpoint of AC. So M will be basically when you invert that, you just get like the tangents. So you take A tangent to like whoops. Okay, so you take that tangent. C tangent. Okay. And now you get these two, I think. I can't even tell which one is this. Just move it around a bit.
The bottom one.
That's the tangent.
Yeah.
Okay, there we go. Oops. No. So these two, and then I'll name them M and N. This one's N. Okay, and then finally we have the circumcircle of POM and QON intersect again at Z. So you'll notice that POM and QON, they both pass through the center, so they're lines again. So PM and QN. And then that's Z. That's Z over here. Oops. It's this one. It's really far away. I need to bring it closer. Okay, yeah, that's the diagram. The inverted diagram. Okay, finally, we have it. And we want to prove that in the original diagram, Z is like, how do I make this like less cancer to look at? Okay, I think that's a bit better. Maybe. Yeah, we want to prove ZO is parallel to BC, which is still going to be true because after inverting, because ZO passes through the center. Okay, so that's what we want to prove. So if you notice, there's an awful lot of lines here. In fact, there's like no circles. Literally no circles. There's only the circumcircle, which is never used. Except for the tangent C. but that's just angle conditions. So it's actually like basically projective, right? It's just a projective problem. And I noticed that like, oh, it's actually literally completely projective. So yes, what does it come down to trying to prove that ZO is parallel to BC? It's basically like saying that if you draw the line through O parallel to BC, then these two lines are concurrent on there. Right? So they're all concurrent at Z. So that's basically what it's saying. So yeah. I guess maybe I should. Okay, I'm just gonna like draw stuff.
Like PM.
Yeah. So
QN and something else.
PM, QN, and this line. That it's gonna be this one,
the tangent line.
This one, and this one, which we'll define as like parallel to BC.
Oh.
So basically defining these three lines and saying, if we prove these three are concurrent, that's the problem. Right. Yeah, that's what it's saying. And I guess proving concurrency in projective is easier because like you can do cross ratio chase, and that's actually exactly what I ended up doing. But not exactly, right? It's not exactly what I did, of course. So so I basically noticed that it was literally like an MMP. So when Lucas and Michael introduced to me MMP, they were talking about it like in terms of cross ratios. So if you have like one line and then another line, right? And then if you have like 4 points on there, and then you have another 4 points on the other line, and then there's like some sort of combination of transformations that basically like take projective transformations, like these elementary correspondences between lines. The points on the lines. So say it like takes this to this, this to this, this to this. Then you actually know what this is. This fourth point is because 3 points determine the projective transformation of the line. Yeah, on one dimension. So basically, if you manage to get 3 points over, yeah. So these arrows might be like several elementary correspondence, several pencils as they call it, like camp or whatever. But yeah. It might be several of them, but no matter what, if you can find this kind of thing, then you can determine the fourth point. And I guess the whole point of the MMP that I was introduced to was that if you can find 3 special cases of points where that is easier to prove, then you can actually prove it for everything if you manage to prove that the result is just a projective transformation, 1D projective transformation of the original. Moving point, I guess, right? So that's the version I was introduced to. So you might be worried thinking here, hey, you're not allowed to use MMP in DJGO, right? So that's a little bit worrying. But luckily at camp, I heard people talking about the degrees of MMP. I realized, it's not really a projective thing. It's actually more like a complex bash / chord bash thing. I don't know. Where you try to find like a point in terms of another point, like as a polynomial in terms of another point or something. I guess I think that's how it is, and then you find enough points so that it fixes the polynomial, or something like that.
Bigger than order of the degree.
Yeah. So then you know the polynomial, and then so that was what, like, I guess maybe that's what actual MMP is. So I realized this isn't really the strongest form of MMP. In fact, you don't even have to state this in terms of MMP, as I'll explain later. But for now, let's just do it. Like, apply this form of MMP, this weak form of MMP here. So, obviously, we don't know Z is, like, actually here. So I'm just going to define X and Y. So X, let's let that be, like, PM intersect. I'm just going to call this line L. And then Y equals QN intersect L. And so my claim is that there's like a sequence of elementary correspondences from X to Y. That's pretty cool. And so like when X moves, Y moves with it in a sort of like in a sort of projective way on this line L, basically. Alright, so I'm going to basically explain that. And it turns out, like, basically, because when you take project transformations, you're taking it, like, taking the pencil through a point. But it turns out all these points are fixed when you're moving this variable line here. So that's pretty cool. So, yeah. So we go from L, we're at X. Well, PM intersect L, right? Okay, let's have a look. Let me try and figure this out. So this is X and Y. Our goal is to prove X and Y are the same point, but we don't know yet. So, where does it go from X? So X is on PM. So I'm gonna project it from have a look. So I think it's projecting it through M to P. Yeah, okay. Okay. So project through M to P. And we're projecting it onto this BO line. Okay. I think that's how it works. And those BO is like fixed with respect to this triangle. So basically, like, I want to make sure everything's fixed. Right. So M is fixed, BO is fixed. L is also fixed because we constructed it as the parallel line through O to BC. Okay, what's the next one? The next one is the obvious one. We go through A to reach Q, right? I'm just gonna delete this XY thing. To reach Q, and then we're gonna go on to line CO this time. And finally, we're basically doing like conjugate. We're like reversing all our steps.
Yeah.
And then finally, we go through N this time to Y on L. So that is the sequence of pencil/elementary correspondences that we're gonna do to get from X to Y. And since we want to prove that X and Y are the same point, it suffices to prove that this whole thing is the identity, right? So, yeah, and so basically we want to just find 3 special points where it's easy to prove that this is the identity. So 3 special points on L where it's easy to prove that it goes to itself, and then we're done, because MMP. Well, very weak MMP, right? Okay, so the first one I thought of was like, if we just took this tangent, right? We just took the tangent line. I think that's what I did, right? Okay. So I think it's this point. Yeah, I think it's this point. Unless I'm mistaken. Is it? Let me have a look. Let me check my list, because like, not actually sure which thing it is. Oh, this is. Yeah, have a look. Okay, I'm not sure which one it is because it's kind of confusing. But have a look. So. Check. Oh. I'm just trying to see like where everything is in this diagram. This might not match.
So we're looking for 3 points on like L.
Go to BO.
Oh, you get what's going on, right?
Yeah, I'm trying to find.
We're looking for 3 points on L, for which this is obviously the identity.
What did I do? Let me see. I think. Oh, it's like really hard to see because it's like really aids. Damn it. This is tough because it just everything just looks the same. Might be a bit of a problem. It's even a. Is this even a real solve? I don't know. Okay, I think the problem with this diagram right now is that everything, like these two lines look a bit parallel, so maybe I have to like move it. Just gonna move this so it's like less parallel. Hold on. Okay, so now again, not this point anymore then. Damn it. This is very hard. It's hard to see anything. Oops. Okay, so I think it's this point. Alright. So now we're basically taking the tangent and we're letting it meet L. And then we project it through M onto BO, so it goes here. Like here. And then we're projecting it through A, so it goes on CO, I think.
Yeah. To Q. And then through N.
Wait, hold on, let me check. To CO. Wait, no, but then it's just really stupid. Yeah. Okay, so basically, like, it's really dumb, right? So you're projecting from this point, intersection point, to here to meet BO. Then you're projecting through N to CO. So that goes here. And then you're projecting... Wait, no, you're projecting through A to CO. And then you're projecting through N onto the line again. So it just goes back, right? Like, all these points, it's just on the same line. Alright, so, yeah, okay. So this is our X. And then it goes through M to here on BO, through A to here on CO, and then through N, which is here, to the line again. This is like the dumbest thing ever.
Oh.
It's literally just like when you project, it just keeps staying on the same line. So this is that special case, right? But you can see how under this whole thing,
So is this the special case where...
it's the special case where like I just let it be where the tangent meets L, the tangent line. But yeah, when you do that, it just keeps staying on the same line and then returning to the original point. So clearly for this point, this thing is the identity, right? So that's good. It's very nice. So we managed to do that. Okay. Okay, so what's the another point? I just picked O itself. This is the best one because you do nothing, right? So notice how L, BO, and CO all pass through O, which means that when you project it, nothing happens ever. So it goes to itself. Yeah, so O is obvious. The last one, obviously, this problem's not free, so we actually have to do something. Like we can't just have everything for free. So it's like, yeah, okay. So this is the one where I do actual geometry instead of just this stuff. All right, let's go. So final one I picked is the point at infinity on L because I thought it would be fitting. So yeah, basically when you do the point at infinity, right? Like point at, let's do infinity, like here, somewhere here, on this line. Okay, so where does that? We need to project. Ah, crap! This drawing is very. Okay, wait, hold on. I think I know that there's a tool that allows me to do stuff. Hold on. Is that Shift? Alt? Okay, wait.
Oh, what just happened?
Oh, I just slept. Whoops.
Right.
Okay. Whatever. I was just trying to make this small. Because then I can move it away and then you can see it properly. It's the cursor. Just go close it. Okay. Alright. Okay, there we go. Nice. Okay, so now, yeah, so I picked the point at infinity. Now I have to. Okay. Wait, how do I annotate? Crap. There we go. I have to move this stuff like out of the way to some free space so you can actually see over here. There we go. That looks better. Nice.
That's pretty cool.
All right, now here's the actual geometry part. So I did the point at infinity because I thought it would be nice. So what happens? So we take the point at infinity, right? And then it goes through M to BO. So let's go into GeoGebra and construct that. So we actually have to construct basically a parallel line now because it's the point at infinity. So it's going to be parallel to L through M on BO. Oh no, it's like almost concurrent. Okay. And then it goes through A. And then onto CO and then Q. Okay, so basically what we want to prove is that it goes to itself, right? So we want to take this point at infinity, and then I'm going to do the reverse projection of this last one, which is basically just doing the same thing on the other side. I'm going to construct a parallel line through N, parallel to L, put it on CO, and then have this point. So we have E and F. And basically what we want to prove is that E, A, and F are collinear. Because if they are collinear, then this whole thing works, right? So then if they're collinear, then the point at infinity goes to E through, so it goes through M to E, and then it goes through A to F, and then it goes through and then it goes through F to the point of infinity. Goes through N to the point of infinity. So that's what I want to happen. So I want to prove EAF is collinear. So now here's the actual geometry part where I prove where I prove it's collinear. All right. So I gotta hide a lot of stuff because otherwise it's going to get really jank and not look good. Can I hide multiple things? Yeah, I can. I think so. Yeah, I'm basically just hiding everything to do with the original point. How do I? Hold on. Can I hide like these?
Just like the show just hide tool.
Oh wait. Wait. Show your eye. Okay. Okay, nice. I'm gonna hide a bunch of stuff. Basically, the stuff that relates to the actual Z itself, because we don't care about it. I don't think. What is that? Yeah. Okay. Like the actual Z, we don't care about it. We just care about We don't care about these guys. What else don't we care about? We don't care about P and Q because they're specific to Z. I think that's it, right? Now it looks a lot cleaner. Yeah, okay, nice. So basically, what have I done? I just drew okay, I took ABC, I constructed the tangents to M and N, and then I drew parallel lines M and N through M and N, parallel to L, which is parallel to BC. So these parallel lines. And I made them meet BO and CO at E and F. Need to move just a little bit more to make E not look collinear. Okay, nice. And I want to prove that FAE is collinear. That's literally all I have to do. So what do I do now?
So the definition of E is like there's a parallel line through M to BC, and it hits BO at E, right? That's the definition of E.
Yes. And then definition of F is similar.
It's going through
going through N and then hits CO.
Parallel to BC.
Yeah.
And it hits CO at F.
Yeah. So that's how I'm defining everything. And I just want to prove FAE is collinear. So now it's just like normal geometry. We actually have to do normal geometry in this problem. Oh no.
Oh.
So
that's like the lemma. That's like one of the like the lemma.
Okay, so how do I do it? I just do the angle chase, I guess. I don't know. Firstly, notice that like this is a right angle because it's just the radius and the tangent. This is also a right angle.
That's pretty nice. So it's like suffices to prove.
Yeah.
This is special.
Yeah. Okay. And then what do I do next? Oh yeah, these two are equal because like it's isosceles. VOC is isosceles. Yeah, and then it's equal to this, and also this. So what does that mean? It means that MBE, whoops, MBE and this NCF are like similar. Because they got the right angle and they got the other angle. So now, let's have a look. So now we take, this is really messy. Now we take MA. MA is equal to MB. And MB is of a certain ratio to ME. Right? So we know the ratio MA to ME equals MB to ME. Similarly, NA is equal to NC. We know it's of the same ratio to NF due to the similar triangles. So basically, AM to A equals AN to NF. AM to ME equals AN to NF. Same ratio. We know these two angles are equal because it's alternate. So wow, MAE and NAF are by SAS are similar. And so then this is just collinear. No. Yeah, that's the geometry part. We managed to prove FAE is collinear. Do I write this down properly?
Right. Can we chase through? So once we got the collinear, you said that proves that the point at infinity goes to itself, right?
Yeah. So I'm just gonna like delete the stuff and then just draw that thing on here. Okay, let's just go through it again. But except this time we have this line. Whoops. We have this line, and it's collinear, so it's all good. Right. Okay, so now what happens is the point at infinity. Project point at infinity on L through M to BO. Through M to BO to get E.
Yeah.
Infinity goes to E. E goes through A
CO.
to CO, which is F. And F goes through N, is parallel as well to point at infinity.
Oh, okay.
So now it works. Yeah.
Does that make sense? Yeah.
I was dead for like the last.
Damn it.
Oh, you should have got the last bit, because that last bit's just like it's actually a nice little lemma on its own. Like,
yeah.
So you have a circle, right? Yeah. You got M defined to be the intersection of the tangents, and so is N, right? Yeah. Okay, and then you draw a line parallel to BC going through M. Yeah. Yeah. And it meets BO at E. Yeah. And you draw a line parallel to BC going through N. Yeah. And it meets CO at F. Yeah. Okay. Okay, and then you prove that AEF are collinear. So that's like the nice little lemma that came out of this.
Yeah. So that's the lemma that allows us to show that the point at infinity goes to the point at infinity in this. So yeah, now we have the point at infinity goes to the point at infinity, O goes to O, and this, whoops, this point over here, that where the tangent meets it, goes to itself. So that's pretty nice. Also, we know that different points because, yeah, we do know that. Okay, unless it's isosceles, but if it's isosceles, then basically in the original question, Z is O, so it's not really well defined. Anyways. So yeah, that's it. So now the problem is solved, right? Because for all, now we've proved that it's literally, this thing is the identity. is the identity. So every point goes to itself, which means that the lines are concurrent. But the problem is, of course, that I haven't resolved the MMP thing, right? MMP thing. So I'm not allowed to use MMP. That's a no-go. Indeed.
It's an NDG or MMP.
Yeah. So that's illegal. So basically, I have to not use MMP somehow. Luckily, this is a pretty weak version of MMP, so I can actually just express it in terms of stuff that isn't. It's clearly not off limits. So let's re-show everything that I just hid. Oh god, now it looks really messy.
Can you close that?
Oh god.
Front?
Okay.
Pizza box. Can you close it?
Okay, I guess the first thing I'm gonna do is just I'm gonna define all the points that I didn't define before in my thing, because I think I didn't define a lot of stuff that was supposed to be defined. Alright, so first thing is the what was it again? It was called oh yeah, so the point where the tangent meets it meets line L, right? So I'm gonna have to define that. I'm literally just gonna use whatever name it gives me. It's G now. Okay, and then it goes through M to BO. So I'm gonna have to define GM intersect BO, which is over here. Okay, and then it goes through A to CO. So I'm gonna have to define this tangent line intersects CO. Here it's I don't know, I'm just going with the names that it gives me. And then, of course, it goes back to G through N, so that's nice. Okay, and then what else do I have to define? So, oh, I don't have to define anything for O, because it just goes to itself. Just keeps going to itself. Right, and I've already defined E and F, I think. Okay, yeah, okay. So I'm all ready now. So basically, because this is such a weak version of MMP, I can just, like, phrase it in terms of a cross-ratio chase, right? Because if you think about it, I just took the point Z and, like, 4 other points and just cross-ratio chased it to itself.
So literally like the proof of MMP.
So, and also cross-ratios are not off limits on DJGO because they had a harmonic question. So that's clearly not illegal.
Pretty sure the only things that are illegal are like MMP. And
so yeah, this was not in fact MMP. It was actually just stuff that I already knew. Okay, so what are our points? Our points are X. X.
So that's where
this is X.
Tangent, G is where the tangent.
X is defined as PM intersect L. This is L. PM.
Oh, what was that?
P is here. It's like BO intersect the line, just an arbitrary line. 3A. Yeah, this line is variable, so yeah. Okay. So we're basically taking X, we're taking G, O, and the point at infinity. Right? And we're just gonna take the cross ratio and we're just gonna chase it around. So now we just do like this. X G O L infinity. Okay. Equals through M. What was it again? So X goes to X through M goes to P. Okay, I literally wrote this. P. G goes to H, I think. Yeah, I think it's H.
Yeah.
H. O goes to O. Line at infinity goes to, point at infinity goes to it's through M, so it's gonna go through E. Goes through A. This is gonna be Q. Wait, what is okay? So H goes to goes through A to I. O F, and then finally through N it goes to Q. Okay, Q goes to Y through N. Wait, and then I goes to G again. O, and then finally N is over here, so it's gonna go to the take F to infinity. That way. Okay, and then X equals Y, and we're done. So yeah, look, no MMP.
Very good.
So yeah, like as Johnny was saying, like who even uses not harmonic? Like this is not harmonic cross ratio.
Oh yeah, what's he talking about?
Yeah, because like me and Paul are like, bro, where's the cross ratios in the projective lecture? And he was like, bro, who even uses cross ratios that are harmonic?
What?
Wait, who is
I'm
this
like-
Johnny guy?